Yeah, I just want to talk about some attention mechanisms in deep learning. We all know that attention mechanisms are very prevalent in transformer architectures these days. But attention mechanisms started in sequence to sequence models maybe some 8 years ago or something like that. And then there are other use cases of attention mechanisms other than the transformers that we are familiar with. So maybe, so I just want to talk about general attention mechanisms in deep learning, how they started and then how they're implemented in transformers, and then maybe what is the future of them, and so on. So I'm thinking, so in the slides, at least in the slides that I prepared, these are the index. These are the points I want to touch on. To start with, I'll just start with the first formulation of attention mechanism, which is proposed in machine translation as a sequence to sequence model. I'll start with that. And then very similarly, there is attention mechanism in image captioning as well. And then after that, I'll go into attention mechanism or attention use cases in sequence classification for mostly the interpretability of the model. These things we used it previously as well. And then after these three formulations of attention mechanism, I want to talk about a general formulation of attention mechanism, which is popularized in transformer paper. Attention is all you need paper. So that formulation with queries and then keys and then values, it's very intuitive, and then it has a lot of variations. A lot of variants can be derived from the general formulation. So it would be good to know that general formulation. I'll just touch upon that. And then so whenever we use this attention, we usually use this attention as a multi-headed attention. Now we'll talk about what it is. And then in all the cases where attention is used, usually we use multi-headed attention. We'll touch upon there. And then even in the sequence to sequence transformers, and then the first formulation of transformers itself, there are two kinds of attention. One is self-attention and then other is cross-attention. I just want to give some differences and then what are different types of attentions in that topic. And then at the end, I just want to talk about versatility of these attention mechanisms, the different variants we can formulate with these in this framework, and then why they are very prevalent in transformers, and then why they are very good for pre-training, and then why they are subsuming CNNs and then RNNs and so on. And then yeah, so last slide, which is talking about some state-of-the-art architectures, which are transformers, and then which in turn has attention mechanisms solely. So yeah, so I just want to talk about these things in the coming slides, just so that you all know what's coming. Yeah, so this is, so okay, there is a lot of information in this slide, but let me tell you where to focus first and then where to go on after that. So this is the formulation of the first formulation of attention mechanism in sequence to sequence models. Usually if you focus on these green and then red vectors here, and then this is a encoder and then this is a decoder. Usually sequence to sequence models has some encoder, and then it will encode all the encoder sequence into a vector, and then from that vector it will decode the decoded sequence or the output sequence. So here in this case, I saw a cat on mat written in some Japanese or Chinese, I don't know, in some other language. And then the task here is from this language, we have to translate that sentence into English. So this is the snapshot when we are actually doing that decoding. It decoded 3 words and then it is about to decode cat. So this is the encoder and then decoder. So this is the attention mechanism they're talking about. So let's not focus on that right away. But in a usual sequence to sequence model, we don't have this attention mechanism, this thing on top of these encoder and decoder. We'll just encode all the input sequence or encoder sequence into one vector and then pass that vector as a starting vector or starting hidden state for the decoder. And then decoder has only that vector to focus on to decode all the decode all the tokens in the output. So, but with attention, it can, there is a scope to focus on all the outputs of this encoder rather than only last hidden state of the encoder. So to iterate it again, in a standard sequence to sequence model, the link between encoder and then decoder is just the final hidden state of the encoder. So the line passing here. But if we have attention mechanism in these sequence to sequence or encoder decoder models, then there is a scope to use all the encoder outputs. So these green arrows, we can see them as encoder outputs at each time step, at each word or token. And then this attention mechanism can use all of these encoder outputs, the green arrows, which are visible here. The way it will use is that at a decoder, at every step of decoding, let's say here 4 tokens are already decoded, and then the next token is about to decode. And then we can probably assume that I saw a cat, the next one would be the word cat. So at the point of decoding cat, it is using all the encoder outputs from that encoder when we process the sequence in that encoder. The way it is using is with the attention mechanism. So we can think of attention mechanism as just weighted average of some vectors. So here the encoder had these vectors at each time step. And then what attention mechanism will do is that just take some weighted average of these encoder outputs and then give it as a context vector for this decoder. So let me explain the same thing that I mentioned in this diagram here. So the output is at this point to decode the next token in this decoder, we'll create some context vector. So this is the context vector rather than this vector, and then rather than only using this last hidden state from the encoder and then decoding all the tokens in a decoder with just that input. So here in this time step, for each time step, we'll calculate a new context vector other than the last hidden state. There will definitely be last hidden state, and then apart from that, or along with that last hidden state of the previous decoder step, we'll use some other context vector as well. So this context vector is the output of attention weight. So let's talk about how this context vector is actually calculated. So we just saw that we have this list of vectors, right? For each time step from the encoder, there are these list of vectors, encoder hidden states. So on top of this, so let's so when you focus on this area, and then for this decoder step, so we can have a attention function. It could just be some feed-forward neural network. So which will take encoder state and then decoder state and then gives out some score. That's all it does. Takes 2 vectors and then gives out the score. So if we calculate that for all the hidden states, there will be some scores, right? So take this first green vector and then take this hidden state at this current position. There will be one value here. And then take this encoded hidden state for the same decoder step, and then there would be some value here. And then take this encoded hidden state for that decoder step, and then there would be some value here. So these values, these bar plot, we can say it seems like these are the attention weights that are calculated across encoder steps. So there are, let's say, 6 encoder steps here. The first one is just a EOS taken start initial hidden state. So there are 6 states here, 6 green vectors here. For that 6 green vectors, there are 6 hidden states. And then for that 6 hidden state, there are 6 values of attention values. So the way it created is just like I mentioned just before. So for each hidden state, we'll just see the we'll just take the decoder hidden state and then pass it to this attention function. This attention function might be just feed forward neural network. So for each hidden state, there is a value here. And then at the end, the output will look something like this. So if we have a set of vectors, like here, set of encoder hidden states, we'll have weights on top of all the encoder header states. And then it just so happens that some of the vectors or some of the encoded outputs are actually important rather than all of them. So here in this case, this one seems very important because the attention weight for that is higher. So why is that? So let's say you took this another language or foreign language sentence and then trying to decode it or trying to translate it in English, and then probably the next word is cat, right? In the ground truth, I saw a cat on mat. The next word is cat. When you are decoding the token cat, what is very important in the encoder sequence? So usually the translation of the cat is very important, right? So this phrase here or this word here in that foreign language is the translation for cat. That's what it is labeled as cat. So it's just easy for decoder to focus on only that word and then translate that word. It doesn't have to focus on anything else. That's what it is doing basically. So this token means cat, but it is given that token in another language. And then it is focusing on that word specifically and then trying to decode that word or translate that word specifically. So that's what attention is doing. It will align this output sequence to the input sequence. So when you're translating usually the separate pieces will translate separately, right? There are some cases where we had to translate phrases in different order, but that is a minority case, and then even that is accommodated in this attention mechanism. But the overall idea is to align this output decoding to the input sequence as well. So here in this case, when we are at the point we are about to decode cat, if you do the attention mechanism and then create a context vector, it will concentrate more on the translation of cat rather than other encoder steps. So overall, what we get from this is at each decoder step, we'll focus on some word in the encoder or some word in the input sequence, not all the words, as in the standard sequence to sequence model. So so usually these are the steps that we have to encode in code. We can just go over them just to have a better sense of what's going on in this picture. So all these S1, S2, SM, these are encoded states, the green vectors shown here. And then there is one decoder state because we are doing or calculating all of these attention weight for this particular decoder step. We can do for all the decoder steps, but here we are doing this or doing this, applying this attention mechanism or calculating the attention weight for this time step specifically. So for this time step, just before we are about to predict cat, there is one decoder state, and then there are the input for this attention mechanism, all the encoder states. So S1, S2 until SM are the all encoder states, and then one decoder state. What we do after this is just I mentioned before, use some attention function for every encoder state in encoder state, and then for the decoder state. So the result is this one. So if you had to get score for this decoder state with all the encoder states. So that's why here mentioned K is equal to 1 to M. So you'll get M scores because there are M encoder states by inferring this function. By putting S1 in one case and then S2 in one case and then S3 in one case and so on. So because there are M encoder states, we'll get M scores here. So these M scores are not normalized, non-normalized attention weights. So this is just a normalization step. These scores, right? These scores are the entities. There are M scores like this. K starts from 1 to M. And then to get the attention weight for each of it, we just have to do the softmax. So this is the softmax operation. This is just doing the exponential and then normalizing it. So this is the sum of all the exponentials, and then this is the exponential of that particular time step or that T. So this T or K could be 1 to M. So this is just a softmax equation. And then after getting these attention weights is just weighted average, as we mentioned before. So a weighted average is that A1 at time step T. So K for each K. So K is 1 to M, right? K is the time step of encoder. So there are M time steps here as seen in here. And then we'll get A 1 to M. So that's what it is saying here. So there are M attention weights, and then there are M encoder states. We're just doing weighted average now. So A1, A2, A1 into S1, A2 into S2, and then until AM into SM at the time step of T. We're only seeing one time step, right? We can do this for all the time step in the decoder. We are only seeing this for one decoder time step. So if we do the weighted average, then this is the output of the attention mechanism. This is the context vector that we are talking about, and then we should pass to this decoder. So the general thing that I want you to focus here is that for each decoder step, we are calculating attention weights and then taking the weighted average of these encoder outputs based on that attention weights. So we can see this decoder state, this decoder step, the time step in the decoder at which we are calculating these attention weights as a query, and then these encoder outputs as values, right? We can see like that because one query is compared against all the vectors here and then creating a weighted average of some values. So in that sense, we can see this decoder stat as query and then all of these encoder states as values. So this queries, values, and then keys will get into more formalization in coming slides. But all we have to understand from this slide is that when we are in the sequence to sequence model, when we are decoding, at each time step of the decoding, we'll compute attention weights, and then based on that attention weights, we'll take the weighted average of all the encoder outputs. That's what it is doing. So this context vector that we are going to pass to this decoder for each step, will be the product of that attention mechanism. Yeah. So you can, yeah, so this is one example of attention mechanism after applied for machine translation. So let's say this is probably this is a French sentence, and then this is the English sentence. There is a translation from French to English. The sentence is actually the agreement on the European Economic Area was signed in August 1992. So this is the one that we had to translate, right? And then see on which words it is translating when it actually decoding. So when the is decoded, it is concentrating on the L word. And then when agreement is decoded, it is concentrating on the accord, because in French, agreement means accord. And then interestingly, see this one. When it is decoding European, the actual time step is zone, but it is actually focusing on some other time step, the European, which is the actual translation of European. So for European, it is concentrating on the right word that it has to translate. And then for economic also, it is focusing on the right word to translate. And same goes for sign, and then August, and then 1992. So the aspect that we are giving to this model with this attention mechanism is that at each decoder step, at each step of translating this sentence, will only focus on some part of the output, some part of the input. So let's say when you are decoding European, you'll only focus on the actual translation of that European in French. So this is the sense of attention. So when doing something, if there are n number of points or n number of vectors or n amount of information, we'll only focus on some information. As in here, at each decoding step, we are focusing on only some steps of the encoder, as represented by these white boxes. So we'll do this. We'll kind of get to this kind of intuition later as well, as we're seeing more and more attention mechanisms. But that's the way we should look at this attention mechanism. At anywhere, there should be query, and then so if there are n entities, we'll just focus on some entities rather than all the entities. So yeah, so just like the attention in sequence to sequence models, if you have a, let's talk about image captioning. So there would be an image, and then based on that image, we have to predict the caption for that image. So caption is a sequence of words, right? So we'll just decoder is same for this case as well. So in the decoder is same as same in mission image captioning, and then same in mission translation as well. So because decoder is just have to generate some words, right? But in image captioning, yeah, meeting will end in 10 minutes. Okay, so I'll try to wrap this up, or maybe we can join to the same link after it is over. So so keep that in mind. So we'll at some point in 9 minutes we'll all pushed out of this meeting, and then we can join back from this on the same meeting as well. Yeah, so we saw sequence to sequence models in mission translation. And then if we talk about the case of image captioning, the decoder is same in both the cases, but the encoder is different. In mission translation, the encoder is sequential encoder, and then in image captioning, because there are images, the encoder would be visual encoder. But still, here also we can treat the feature map of a visual encoder as a bunch of vectors, right? Just like we treated encoder outputs as bunch of vectors. So here also we can, with the same mechanism, at each decoding step, we can find the attention on different areas of the image, and then get some attention maps on image like this. So the only difference here in image captioning, there in mission translation, is that the encoder there is sequential, and then encoder here is visual. So that's why in mission translation, the attention weights are over a sequence, and then here the attention weights are over an image. So one interesting thing here is that, so this is a attention map when we are actually predicting the word frisbee. So you can see that when we are predicting frisbee, there is more focus on frisbee here. The red thing here is frisbee. They both are playing frisbee, so usually, at least in the case when it is predicting frisbee, it is focusing on frisbee. And then when it is predicting a woman, it is focusing on woman on the shade. So at each decoding step, the summary is basically same for this also. The objective is basically same. At each decoding step, focus on only some area of the image, not all the parts of the image. And then it's the same for sequence classification also. But here, as we're seeing in the two cases, the decoder hidden state for some particular time step is the query, right? Here, if you have last hidden state as the query, then it will become attention mechanism for sequence classification. So let's say we have the sequence, and then the task at hand for us is sentiment analysis. So there are sentences like this, and then we have to predict whether the sentiment of this is 1 or 0. So here in this case, when we are so take any RNN or LSTM or any kind of sequential model. After passing a sequence, you'll get final hidden state, right? If you take that final hidden state as the query, and then compute the attention weight over all the tokens that came before, then we get something like this. So where if the sentence is actually positive, it will highlight all the tokens or all the words which are actually impacting the model to predict as positive. So here, a bit intuitively, these words which are talking about the goodness of the restaurant or the dishes that restaurant provides are highlighted as the signals, or as the things, or as the words that impact the model probability. So here, this is a good sentence. The sentiment is good here, and then the interpretability of the model is that, or the reasons for that good prediction or positive prediction is these words: awesome, and then good, and then pretty, and then best, and then so on. So you can use this attention mechanism for kind of interpretability aspects also for our models. So yeah, so at this point, I just want to go into some general formulation of attention mechanism. So we are talking about queries and then values, right? If you just generalize this formulation as researchers did in that transformer paper, so attention is a function which will take a set of queries and then set of keys and then set of values and then give out a set of vectors as output. That's what it does, the attention mechanism. And then for simplicity's sake, we can take that, we can assume that all of the shapes for all of these matrices is n cross d, where n are the number of vectors. So let's say the number of encoder states or the number of things we have in these visual encoder or the number of time step in sequence classification. So n is number of vectors that we have, and then d is the dimensionality of that vector. So that this could be 10 cross 512 or something like that. 10 is the number of time steps, and then 512 is the dimension of the vector, dimensionality of a vector. So yeah, so there is a general formulation where every attention mechanism will have queries, set of queries, and then set of keys, and then set of values. Sometimes we have to note that sometimes keys and values might come from same set of vectors, and then sometimes all three of them might come from same set of vectors. We'll talk about that in the coming slides. But we'll have these three separate things, but we don't have to have these three separate things as separate. So we can derive these separate things from just one set of vectors as well. So as in the case here, so this is one. So this is the actual diagram of transformer in the paper. In the paper, what they basically say is that there would be queries, keys, and then values, and then at the end there would be some output. So these two diagrams are just the explanation, a bit more detailed explanation of this process. So let's start from the bottom right. So let's say our sentence we are processing with the transformer is Anthony Hopkins admired Michael Bay as a great director. So if you tokenize this thing, just simply take all the words which are space separated, you'll get these number of words. So here there are 9 words. So we are processing a sequence of 9 words. And then if you see this, just beside every word, there is a bracket here, right? So that is representing a vector, basically the word vectors. So Anthony has some word vector, and then Hopkins has one word vector, and then admired has some word vector. So if you see this, this is a matrix, and then the dimensionality of this matrix would be 9 cross the dimensionality of the vector, right? So if the word vector or word embedding dimensions is 64, then this matrix, which is the input for our transformer, would be 9 cross 64. 9 is the number of tokens in our sequence, and then 64 is the length of the vector. So so this is the output that we have. So we don't have keys and then queries and then keys and then values separately. So this is what we give for a transformer, right? It's just a set of word vectors. That's all we give. So we can add some Persian vectors as well, Persian embeddings and then that information as well. But for a simplicity case, let's leave that. So the input for a transformer to process a sequence is just 9 vectors. So here vector size is 64, and there's 9 vectors. So here what they are depicting is that we can get queries and then keys and then values from just these 9 vectors. How? Just to so we can just have different linear layers feed for neural networks to create these queries and then keys and then values. So this is the particular case of self-attention, where all the queries and then keys and then values are coming from the same set of vectors. So we are just starting from same set of word embeddings, right? And then we'll create these queries and then keys and then values from the same set by using different feed forward neural networks. So after getting these queries Q, K, and then V, we'll do this scale dot product addition. So we'll talk about how this scale dot product addition works just in a minute. Yeah, so let me start from where I stopped in the last session. So we'll have this set of word vectors, word openings for each word. And then before doing attention, we'll create these queries and then keys and then values with different feed forward neural networks. So from one set of vectors, we are creating 3 sets of vectors. And then if we have these 3 sets of vectors, we can do attention. The way attention works is this. So we'll take the queries and then matrix multiply with keys, which is basically doing the dot product between these queries and then keys. So we'll see the zoom version of that in the next slide with the dimensions and then with the actual operations happening. We'll talk about that. So usually all these queries will just do the dot product with these keys and then divide it by square root of the dimensions. So this will give the attention weights for every pair of positions. If we have 9 pairs here, so the output for this is for this q cross k would be 9 cross 9. So we'll see the dimensions in the next slide. And so if we have this 9 cross 9 matrix, we'll just multiply that with V. So 9 cross 9 is just a weights of attention, weights for each position. We have 9 position and then nine positions to see the attention for. That's why we have 9 cross 9. And then if you just multiply the 9 cross 9 vector with the V, the set of values, we'll get the output. So we'll see the dimensions in the next slide. But the overall, how attention works is that take the queries and then do the matrix multiplication with keys first. And then with that product, do the matrix multiplication of values after that. And the output and the input for these is just Q and then K and then V. And then in this case of self-attention for the transformer, all these different sets of vectors are coming from the same word embeddings. So yeah, any questions here? I'm not giving time for questions, but any questions here? Any clarification needed? Maybe this will give a bit more clarity. Sorry. So this will give.
Prabhu,
yeah.
So can you explain the difference between K and V?
K and V. Okay. Here. Okay.
So in the previous diagram, so there was no V, right? There was only K in the LSTM.
Okay. Yeah, we'll get to that, I guess. So here there are only V and then there are only Q, right? That's what you're saying, right, Ujjwal? There is no K in the previous examples.
Yes.
Oh yeah. So yeah, we'll get to that. So usually, okay, so maybe I can answer a bit there as well.
Fine. If you plan later, we can discuss them.
Okay. Yeah. Yeah. So why we have keys is that to act as some attention function or something. So here we have attention function, which is a feed forward neural network, right? So here the attention function is feed forward neural network. So this is the value, and then this is the query, and then to take these two vectors and then get a square, get a score between these two vectors, we are using this attention function, and then this is a feed forward neural network. And then, so instead of that, what it does in the transformer is use the formulation of the keys. So we'll get separate keys for each of these values, and then use that keys for do the dot product. So there is no feed forward neural network, but we have this formulation of keys, which came from values, which is derived from the same values. So with that key formulation is just a way of calculating these scores. So values are the values are the things that we do the weighted average with, and then keys are the things that we do the dot product with, and then get the attention weights. So here we don't have keys because we're using this attention function to get the scores.
So why are we separately? Why not just one? We can use the same to.
Yeah, we can do the same. We can do the same, but this is the original formulation of attention that in this 2015 paper they proposed. So this queries and then keys and then value formulation came only at 2017 or 2018 with the transformer paper. So we can still do that transformer type of attention here as well. It's just easy, right? It's just these are the queries and then these are the values. Get some keys, use some neural network, separate neural network to get keys from these values and then use those keys to do the dot product and then get the attention weights. So we can use that attention here as well. But yeah, it's just the first formulation of attention mechanism that is proposed in 2015. That answers answers the question a bit. Maybe we can discuss more as well. But yeah, these are just two different formulations. And then the idea of keys and values and then queries didn't come yet at this point. So that's why these are values. If you look back, these are the values and then these are the queries. And then they're finding another way to get the scores, not the key formulation. Taking the keys and then doing the dot products between keys and then queries and stuff.
So this is a different formulation right, from the one that we discussed.
Yes. Yeah. It's just that this keys formulation is a bit general. It can be used in the previous things as well. But yeah, it is different formulation. So that's why we don't have keys.
Hello, Ujjwal. Hello.
Yeah, somebody is calling Ujjwal.
Yeah, Gayatri here.
Gayatri, yeah.
Yeah, so Ujjwal, can you please repeat your question? I want to hear it. Means what did you just ask?
Asking the difference between key and values, right? So what is key and what is values? It's written in the formulation.
No, after that you are saying that. What?
And why it was not there in the first formulation?
Okay. So the question that Ujjwal is asking is that, so here we have these values, right? These values and then these queries. For each query, there are some values and then there is some way of creating the attention weights. And then after creating attention weights, we'll do the weighted average. The question Ujjwal is asking is, in this formulation, where are the keys? And then why are we using keys right now in transformers? So here, the functionality of the keys is carried out by this attention function to get the scores, to get the attention weights. And then, of course, the key formulation is not done at this point in 2015. It's just one way of calculating scores from the values and then queries. And then, at the end, values are the ones that we do the weighted average with, weighted sum with. So that's the question Ujjwal is asking. You hear me?
Hi, Prabhu.
Yeah, sorry for that.
Little better.
Yeah. Okay. Yeah. Sorry for that. This got disconnected. Okay. Never give up. Never surrender, never give up. Okay. So yeah. So the question is why there are no keys here, and then the functionality of the keys is provided by this attention function. So maybe we'll talk about that later. So let's maybe move on, at least for now. You can hear me properly only, right?
Yeah.
Okay. So we have queries and then keys and then values. This is the dot product basically. You do the matrix multiplication of queries and then keys, and then with those attention weights, multiply that attention weights with values. Then we'll get the output. So the way it happens is that, so let's focus on, so maybe focus here. So we already saw that these queries and then keys are coming from the same set of word vectors, right? After transforming them to queries and then keys, so they still will be associated with the same tokens. So even though the vectors are different than the word vectors, these different vectors, the different query vectors and the different key vectors are associated with the same tokens, right? So there are 9 tokens and then 9 tokens. So what we are doing is just doing the dot product between each of these things. So there are 9 and then 9. If you do the matrix multiplication, basically this is 9 cross 64, and then this is 64 cross 9. If you matrix multiply these two matrices, you'll get 9 cross 9. And then you can see it as a vector operation also. If you take one row here and then do the dot product with the column here, then you will get this weight. So basically that's what matrix multiplication is, right? So let me close this statement. So I guess what you're talking is we have these queries and then keys and then some kind of matrix multiplication, right? After this matrix multiplication, we'll get weights. And then if you do the matrix multiplication again, and then we'll basically get the weighted sum of these values. So so this is a matrix multiplication between queries and then keys. What it is actually doing is that for each query, it is doing the dot product with each of the keys and then getting these weights. So as we saw previously, these are just. So is that okay? Can you hear me?
Yeah, it's better.
Okay.
Prabhu, you can go ahead. If there is any disturbance, I'll inform.
Okay. Yeah, that's good. So you can think of this as a matrix multiplication is just a dot product between vectors, right? So here we have these Q matrix, and then the first row of this Q matrix will get dot product, will get to calculate dot product with the first column of this K. And then that actually means that the Anthony query is dot product with Anthony key. So what is the weight for that? That is the value represented here. And then if you do for all of the rows and then all of the columns here, we'll get these weight matrix. So we can do the heat map also here. It's basically, you can see the diagonal values have more values, right? Because it is attending to itself a bit more than the other things. But there are other attention weights also, which are not diagonally spaced. So some of these things, some of the tokens here will be attended to some other tokens as well, based on these attention values. So yeah, so we'll just do this division by square root of dk for effective training purposes, and then kind of having the same scale or something like that. And then after that, we'll do the softmax, because these dot product values won't be normalized, right? But for each token, we need the attention weights, and then attention weights are basically normalized, should be normalized. So if they're not normalized, it doesn't make sense. So for example, the ideal output would be, so for this Anthony token, there would be a list of attention weights for the nine places that we are looking for. And then for Hopkins, there would be 9 values. For Admire, there would be 9 values. And then for Michael, there would be 9 values. For all of these sets of 9 values are the attention weights across all the steps. And the steps also is the same steps, same tokens. So after this softmax, we'll get attention weights. And then the output, this 9 cross 9, and then this into 9 cross 64 is basically, again, the weighted sum. So these are the weights. And then if you do the matrix multiplication, it will just same as doing the weighted sum. And if you do that weighted sum, you'll end up with 9 cross 64, which is the output that we talked about in the previous slide. So attention takes queries and then keys and then values, and then gives out the output matrix. They all have same dimensions, but it's just that we'll calculate the attention weights first with multiplying Q and K, and then do the weighted sum by multiplying that with the V. Yeah, so these are some explanation and with the dimensions. So maybe you can go through it once more. And then yeah, so I didn't give the links or source for all of these diagrams. I'll give the sources for all of these diagrams as well. So if you need more explanation, maybe you can go there, or we can discuss it after. So as I mentioned previously, anytime we use self-attention or attention mechanism, we'll use it in the sense of multi-headed attention only. So let's say here So we started out with these, right? With these green matrix. This green or blue? Okay, blue matrix. This blue matrix has 9 vectors, 9 cross 64. That's what we started out with, right? For each transformer, that's what, if you're processing 9 word vectors, that's what we'll start with. So let's assume we just copied all of them. Maybe how many times? 8 times. Copied all of them 8 times. So these at the end, right? At the end, there are different colors and then different matrices there. They're just copies of the same thing. They're colored differently because we'll use different feed-forward networks, different projections in some sense, and then create multiple sets of QKVs, multiple sets of queries and then keys and values, not just one. So usually in the standard attention, we just created one set of Q and then K and then V, right? So we'll just create 8 sets of them. It's just easy, right? We'll just change or have more feed-forward neural networks and then create more Qs and then more Ks and then more Vs. So here in this case, we have created 8 of them, 8 sets of them, 8 triplets of Q, K, Vs. So and then we can do the same process, scale dot product attention, for each set of queries and then keys and values. That's what they're also doing. And then,
so is there any advantage in first of all, what's the basic advantage, Prabhu, in having this kind of redundancy and having multiple heads, and if we increase the heads let's say infinite to an infinite fashion, right? So
yeah,
does it also help in some way improving the overall architecture stability or such?
Yeah, I guess it will improve. Based on the explanations that I know, there might be more. But one explanation people give is that in the same vector, there are different aspects to focus on. So in some sense, these different projections are focusing on different aspects in the same vector. So that's what people are saying. So if in one sense, let's say, let's talk about dependency parsing, or let's talk about maybe some co-reference resolution or something, right? So there are different sets of information. For those different sets of information, each token has to focus on different sets of tokens. If you just have one attention weights, maybe it's not enough. So that's what people usually give. And then this multi-headed attention with different projection. Each projection will focus on one aspect of it.
So basically, there are multiple aspects in the data, and each head will, because of difference in initializations, each head tend to learn different nuances out of the same data.
Yeah, that's what I would think. I don't have very scientific answer for that, but that's what I read somewhere. I heard people saying. Yeah, usually. So the difference is only the feed-forward neural networks or projection neural networks that we are using for creating these different sets, right? Yeah, based on those different initializations, there would be learning also, right, in between, and then each head tend to learn one aspect of something, of a word or of a image patch or something like that.
I see.
Yeah.
So Q and K also, these are copies, or here also there are, here QKV, right? So I mean, maybe you have explained it, I just missed it. So QK, are these copied, or here also there are different weights, different linear layers to create that scale dot product attention?
Yeah, so here there are 2 different types of neural networks. One is from the sets, from the word vectors, there would be linear layers to create Q and then separate Q and then K and then V. That is one linear layers, one set of linear layers. Okay. And then this set of linear layers is to actually create different Qs and Ks and Vs. So basically here there are 3. Here there would be 3 into 8 times, 3 into 8. 24 neural networks or 24 linear networks.
Otherwise it makes sense. Otherwise representation for itself is always similar, and yes, always its attention will be high, right? Rest of it will be 0 if you normalize.
Yeah, definitely. So having these different installations, different linear layers, is a key, definitely. Yeah. So And then one other, oh God, we are running out of time again. Okay. So 10 minutes, maybe I'll try to finish in 10 minutes. So usually, yeah, so multi-headed attention, it will focus on different aspects of attention. And then one good thing we can get from this is it is easily parallelizable also, right? So we can put these things. So as I would mention in the next slides, we can put each time step in each GPU, and then we can put each head in each GPU, and then and so on. We can do a lot of parallelization. And yeah, so self-attention versus cross-attention. Yeah, Mercy.
Just before you go, what is how is that final linear layer coming up? So
okay. Yeah, I didn't mention that. Yeah, so the yeah, so for each set of Q, K, and then V, there will be one value, right? Weighted sum of values, which is dimension of 64. That's also output is also 9 cross 64. But because we have 8 copies of them or 8 different versions of them, that's also would have 8 different versions, right? And then to bring that back to one version, we'll concatenate all the results and then have some linear and then get to our original 9 cross 60. So we have these 8 versions of queries, keys, and values. 8 versions will get 8 vectors or 8 matrices separately, and then in some dimension we can concatenate them and then have a linear layer and then bring them back to the original dimension. So if there are 8, then that linear function will reduce the dimensionality by 8 because it could be 8 times. Okay. If you're starting with 64, the output, the concatenated output after multi-headed attention would be 8 into 64. And then if the linear layer reduces it by 8 times, then you will finally get 64. So yeah, in all the layers and all the steps, the dimensionality doesn't change anywhere. So we are putting this linear layer and then changing the dimensionality just because we increase that dimensionality into 8 times doing this multi-headed stuff. Yeah. So yeah. So I'll just quickly go through it. So the cases that we are talking about till now is self-attention because of the point that these keys, these queries and then keys and then values are coming from the same set of vectors. If the queries come from different set of vectors, then it's called cross-attention. It's just so this is the original formulation of transformer in sequence to sequence model. This is encoder, the left part. The right part is decoder. And then if you see the multi-head attention in the decoder, the second multi-head attention in the decoder. So there are, okay, let's start here. In the encoder, the input goes 3 ways, right? So that's self-attention because from the input itself, they are creating queries and then keys and then values. That is self-attention. In the encoder, there is self-attention. In the decoder, there is some self-attention, masked self-attention. And then after that, there is cross-attention with the encoder outputs. So two arrows here are signifying keys and values. And then one arrow at the rightmost is signifying queries. So for this multi-head attention, which is a cross-attention in the decoder, the queries are coming from the decoder and the keys and values are coming from the encoder, just like the thing that we saw in the sequence model, the original formulation. So it will kind of have the same effect, same effect. But here we call it cross-attention, and then keys and values will come from encoder, and then queries will come from decoder. Yeah, so that's the difference between self-attention and then cross-attention. Yeah, I guess I kind of finished the slides also. But so I just want to appreciate the versatility of attention mechanism. There are different points, and then I could have spent more time and then put some resources or the papers that are actually talking about them, but I didn't have that much time. But maybe I can put some resources afterwards. But usually these attention mechanisms are subsuming CNNs and then RNNs as well. So these attention mechanisms are approximating 2D filters or feature extractors like the kernels in CNN. They are approximating that as well. And then they are approximating sequential features also, like the features that we get from a LSTM or RNN, the sequential features. And then, so these attention mechanism works well with high-level features and then low-level features as well. So one example is that image GPT has 1 pixel as 1 token, and then BERT has 1 word as 1 token. So we can definitely assume, we can definitely think that 1 word has a lot of meanings than 1 pixel, right? 1 pixel is just not that meaningful when compared to 1 word. So even though these the meaning, the amount of meaning in 1 token is different, it is still able to find the right patterns in these 2 levels of features as well. And then one other thing is effective scaling. If you keep on increasing the layers, it is scaling and then giving more performance. And then it is scaling in the embedding dimension also. Also in GPT-3, the dimension of the vectors is kind of 20K or something like that, 20K or 30K. So in CNNs or RNNs, we never saw that much of vector length. So it never used to work, or it never used to exploit that length of dimensions or something like that. So so effective scaling in lot of dimensions when we are talking about these attention mechanisms and then transforms. And then because the nature is not sequential.
So what's the fit? I mean, CNN part didn't understand. So if we if the size increases, size of the vector increases, you are saying that it tries to compact, so it might not get all the context of the vector. That's what you mean by CNN not able to handle large representations.
Yeah, I mean, so we have this image, right? If the image is 1000 cross 1000, all the feature vectors or all the feature maps that we get is less than 1000 cross 1000, right? In some sense, even though we increase the timer and stuff. In that sense, I'm saying, but it would be very clear in the RNN case. So let's say in RNN, the length of the vector that we use is usually 512 or 1024, right? And even though if you increase it to 20,000 or 30,000, it doesn't. Yeah, hidden state. Yeah, length of the hidden state. It doesn't exploit that dimensions much, because maybe there is not that much to learn in that RNNs or something like that. So usually, I never saw any RNNs or LSTM with dimensionality more than 1000 or 2000. So, but these transformers these days are having 20,000 or 30,000 dimensions. And then because of these dot products or attention mechanisms, they are exploiting that information as well, that dimension as well, that dimension of scaling as well. That's what I'm trying to say here.
Okay.
Yeah, this is just one of the aspect that I think is going on, and then based on some data, but it's not scientifically grounded, at least this point. But some points are, and so this. Yeah, so after that, non-sequential computation is there. That's why it's easier to parallelize, and then multi-headed addiction, it's easier to parallelize there also. We can put multiple heads in multiple GPUs and stuff. And then availability, it is better for pre-training because of all these reasons. It can scale effectively, and then it can use large data by doing by easily parallelizable, and then take more compute, and then it is nowadays better suited for pre-training, and then all the pre-training things are using transformers and this stuff. And so attention mechanisms are better for mixing the different modalities as well. So in the case of images and text in DALI, and then Perceive.io, where the image modalities are images, text, and then audios, and then the stuff. So it is very good in multi-modal models as well. So, but maybe we'll get to that in some other thing. So this is architecture of Perceive.io. I don't want to go into much detail, but here also it's a combination of self-attention and then cross-attention stuff. And then this is able to process any kind of domain data. This is basically the same thing that we mentioned last time. All these attention mechanisms are in transformers, and then transformers are the state of the art. So I'm seeing this many times. I'm showing this many times because I want you to go into these models and then see their demos at least. Maybe read research papers related to them.